Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, Unit P4, Electricity and Magnetism. And today we're looking at potential dividers. So the learning objective is describe and use potential dividers. And there's some calculations to go alongside that as well. So just as a recap, I've got two circuits here, both 6-volt supplies. Both got a, well, I won't mention it, they've both got a effective resistance. Now, effective resistance just means total resistance. And I thought you'd do some very quick calculations to calculate the current V1, which is voltage across resistor 1, and the voltage across resistor 2 for both of these circuits. I'll give you a few seconds to work them out, pause it, and then see what you get. So you should get the following results. Okay, so they've both got 40 ohms resistance. They've both therefore got the same current flowing through them, but the resistors have got different values of voltage across them. And that's because the majority of the voltage is going to be across the bigger resistor. So, for example, in the second one here, you've got 6 volts. Most of it, 4.5 volts of it, is across the 30 ohm resistor. And on the right here, only a little bit of voltage, or 1.5, or about a quarter of voltage, or exactly a quarter of voltage rather, is across the 10 ohm resistor. And this is something we're going to use today. So this is a potential divider. It splits the potential difference of a power source between two components. And this is the symbol for it. And this is what a potential divider can potentially look like here. And you notice it is basically very, very similar to a, so in fact, this is not a potential divider, so this is a variable resistor, but you use one of them in a potential divider circuit. Okay, and the way it works is, let's say you've got current in here, you've got current out there, you've got a slider. Now, the current goes through this coil of wire. Now, in reality, there'd be hundreds or thousands of coils, but this has just got turns rather. This only got a few on to demonstrate that. And here, it's about roughly a third of the way along the slider. So what that means is, let's say this is 1,000 ohms total resistance. It's about a third of the way along. So it goes through a third of the way. So a third is about 330 ohms. It'll then go to here. Now, this bit here at the top is effectively zero resistance, or very, very, very small resistance. So it will have, like I say, about a third of the maximum resistance, so 330 ohms. If I shift it more this way, then it goes through less of this coil, which is what's causing the resistance. So the resistance drops. If I shift it more to the right, it goes through more of this coil here, goes through more turns, and the effective resistance increases. So, if we were to vary the resistance of the potential of the variable resistor here, then let's have a look at what you might get. So, in fact, or you might get what you would get. You'd obviously have to have an ammeter in there as well if you want to measure the current. And a voltmeter across here, but we're just looking at the brightness. What you'll see is, when I have this on low resistance, then this is very bright. When I've got this on very high resistance, it is quite dim. Even without adding any components in there, like an ammeter, voltmeter, you can't actually see that. Whereas if you add an ammeter and a voltmeter, so you add an ammeter here in series, voltmeter in parallel, what you'll see is when it's on very low resistance here, then you've got most of the voltage across the motor, which is a bit like in the starter task where we had most of the voltage across the big resistor. Because now, if we've got the voltage here low, you've got the resistance of the variable resistor low, then the majority of the voltage is going to be across the motor because the resistance is bigger by comparison. Whereas when I make the variable resistor high resistance, then I've got most of the voltage across the variable resistor. Also, when I make it high resistance, I've got less current, so those two things will combine to make the motor spin quite slowly. So let's get into some of the maths. So a potential divider equation, V1 over V2 equals R1 over R2. And, pardon me, we can rearrange that to get V1. So V1, to be clear, is the voltage across resistor 1, equals R1 over R2 times V in. So that's not a rearrangement. I do apologize, I misworded that. That is looking at the, yeah, that's not rearrangement, sorry, my mistake. This is the potential divider equation here. Now, V in, V naught in this diagram is just the voltage supply. So you can use different letters. You use VS for voltage supply, V in, V0, which we've got in this diagram. Different ways you can represent it. But effectively what it means is from the top equation here, the voltage is proportional, the voltage across the component is proportional to the resistance. So for example, if R2 is twice the size of R1, then the ratio of voltage here, you would have only half as much voltage across V1 as you do across, say, across R1 as you do across R2. So have a go at this question here. Now you can do it, like I say, using Ohm's law, where you work out total resistance, total current, etc. But try it with the voltage divider rule I've just shown you. So V out equals R1 over RT over V times V in. So 12 is the total, sorry, is the value of R1 in this case, or the total resistance of 16 times the supply of 20, or you could say 3/4, which gives you 50 volts. Now, a little bit more of a descriptive question here. Describe how light intensity changes the output. Also, is this a good circuit? So we've got a LDR, light dependent resistor. We've got a bulb, which is in parallel with the resistor here. I just want you to think about, is this a good circuit? Give you a few seconds to think. Okay, and I'll go through the answer now. So as light intensity increases with a thermistor, as we looked at last lesson, resistance decreases. This increases the current, which is good. Well, might be good depending on what we're looking for. It also ensures the high percentage of voltage across the bulb. So as P was IV, then the power to the bulb will increase, and so too will the brightness, which at first glance you might think is good. However, when is it happening? Well, it's happening when light intensity is high. So this bulb is actually switching on when it's bright. So it's actually doing the opposite to what we want. So if you were to think about how to redesign that circuit, then what you would do is you would basically switch it so that the bulb is in parallel with the LDR. So this circuit here. So in a bright environment, the resistance of the LDR decreases, the voltage across the LDR decreases, the voltage across the lamp decreases, so the lamp does not light up. In a dark environment, the resistance of the LDR increases, the voltage across the LDR increases, the voltage across the lamp increases, so the lamp lights up. So this is a much more useful practical circuit. Okay, so now we'll have a look at some MCQ questions where this is used, potential dividers. So the circuit diagram shows a thermistor and a potential divider. A voltmeter is connected across the thermistor. The graph shows how resistance of the thermistor changes with temperature. As the thermistor becomes warmer, what happens to its resistance and what happens to the reading on the voltmeter? So the resistance, when it becomes warmer, it decreases. And as a result, you've got a smaller proportion of the voltage across there, so that will also decrease. So the answer is A. Next question is a bit more of a wordy one. An electrical engineer has made a pair of components P and Q. The resistance of P decreases as the temperature rises. The resistance of Q increases as the temperature rises. The total resistance of P and Q in series remain constant when the temperature changes. The two components are connected in series with a power source supplying a constant current. Which statement is correct? So what I'll do is I'll go through them from the top and see if each one is true or false and how it is true or false. So we've got two components here. The key bit is resistance P decreases, temperature rises. Resistance of Q increases as temperature rises. So what that means is the total resistance stays the same, but the resistance of each individual component changes. So if a temperature change causes a potential difference across P to double, the PD across Q will always half. That is not true. Because, say, for example, we had a 10-volt supply, and initially there was 5 volts across both. If one of them's doubled, that's 10. If one would be half, that would be 2.5. So total would be 12.5. You'd actually have a bigger output than input, which would be impossible. The difference between the potential difference across P and the potential difference across Q does not change with temperature. The total PD doesn't change. However, the difference between them does change, so that's not true. The PD across component P increases as temperature rises. So the resistance of P decreases, temperature rises. So that means as temperature rises, the PD across it will drop. So that's not true. The sum of the potential difference across P and Q, across P and the potential difference across Q does not change with temperature. Well, it does say there the total voltage will remain the same. It's going to be the same as the supply. So it's D, which is true. Next question. Okay, another potential divider circuit. So the circuit diagram shows a thermistor and a potential divider circuit. The two voltmeters X and Y are connected to the circuit. When the temperature of the thermistor increases, its temperature decreases. As the thermistor becomes warmer, what happens to the reading on each voltmeter? So as it gets warmer, the resistance drops. So as the resistance drops, the voltage across Y, or the voltmeter Y, will decrease. That means we've got a larger fraction of the voltage across X. So X will increase while Y will decrease. So the answer is therefore C. Okay. Next question. The diagram shows two resistors used as a potential divider. The reading on the voltmeter is 1.8 volts. What is the resistance of the resistor R? Okay, so now we need to use the equation. Bear with me. So our voltage divider equation, V out equals R. So in this case, it's this R here, divided by R total times V in. Put my numbers in. V out is 1.8 R over RT times 3 the supply. I can take the 3 over at the other side, so I get 1.8 divided by 3, which is 0.6. I can then change it from RT is R plus your 5K. I can then multiply both sides by R plus 5K, so I'm bringing this over to the other side. I get 0.6 R plus 3K equals R. I then subtract the 0.6 R from both sides to get 3K equals 0.4 R. Divide both sides by 0.4 and I get 7.5K. You could also do this, which is the answer C. You could also do this via trial and error, but this is the mathematical way to solve it. But if you weren't as confident with your maths, you could just try each of those values in the potential divider equation and you would get the same answer. Okay. The circuit shown can be completed by inserting components X, by components of X and Y, sorry. The complete circuit is a potential divider in which potential difference across component Y increases when the temperature increases. Which row shows the correct components X and Y? So if we want the voltage here to increase, then what we need is something where the resistance here will decrease with an increase in let's just double check in which potential difference across Y component Y increase when the temperature increases. So if I need something here where the resistance will drop as the temperature increases. So I'm going to put my thermistor here, and here I just need something with a fixed value, so I'm just going to use a resistor. So the answer is D. Next question, and this is the final one. Two resistors, resistance R1 and R2 are used as a potential divider. What's the relationship between R1, R2, and the potential difference V1 and V2? The relationship is they are directly proportional to each other. R1 over R2 is proportional to V1 over V2. It's the equation I gave you earlier. So the answer is D. And that's it for today's lesson. I'll be posting the next lesson soon on domestic electricity. Thank you very much, and I'll see you in the next lesson.